Okay, perfect. Well, thank you so much for joining us at the inaugural Power Electronics Community Meetup. This is a t-shirt that we designed. You guys are the first ones to get a t-shirt each. In the future, we'll have to make people jump through a hoop or something special. This is the first event. Everyone here is a VIP. I'm so excited to see you. First of all, could you please raise your hand if I personally got in touch with you on LinkedIn? And now we're buddies. Thank you. Yes. We're like close friends now. I want you to know, my name is Maya Spivak. I am a marketer. For you guys, what that means is I'm just a regular civilian. I'm not an engineer. And for me, learning about the world of power electronics has been illuminating. Just in this room, I've had a few discussions. We talked about airships. There's somebody building the next Hindenburg, all electric, but not the Hindenburg, way better. Way better, hopefully. 1,000%. We're all rooting for you. We have folks from Arrow, which is one of the largest distributors, right? This is look at me learning about power electronics. I had to ask somebody, we have more than a few people from Cruise and more than a few people from Lucid. And I was like, if we walk into the same room together, not Cruise and Lucid, Tesla and Lucid, is it gonna be a problem? Are we friendly? And apparently, engineering rises way above, just branding. So everyone is friends here. And I really like that vibe. I have spent the last 15 years marketing for software companies. I will tell you, I know. Software developers are different from you guys. Hardware developers arrive on time. Hardware developers make a commitment and show up to the event. It's incredible. I really respect that, and I really appreciate that. So thank you for doing that. So that's enough about me. I would love to introduce our 3 speakers today. The format that we have today is we have Q&A. Most of you actually have submitted questions already when you signed up, registered for your tickets. We have a few of those questions. We're so ready to answer them. I have them on slides. But if you feel inspired as somebody's talking, just raise your hand. I have this microphone. I'll hop up, and you'll say what you want to say. And they're here to answer, right? That's our job today. And then when we're done with the panel, Chema, who is our sponsor for this evening from Frenetic, is going to give a short tech talk. It's going to be pretty fab. So everyone's going to learn something, including me. I've already learned. I feel like I've learned a lot, but now it's your turn to learn even more than you already know. So please introduce yourselves. I would love for you to say your name, what company you're representing, what you do there. That would be great. Ben.
I'm Ben. I work at Tesla Motors. I work on the supercharger team. I am the systems integration lead for the V4, so our new upcoming supercharger.
Hello, I'm Chema Molina. I'm CEO and founder of Frenetic, and I design better magnetics.
This is Shushi, so I come from the Lunar Energy. I lead the electrical engineering team here.
Thank you, everybody. Okay, our first question. One of you guys submitted this question. How are magnetics, which is to say inductors, transformers, common mode choke, playing a role in the GaN and SiC designs? Did I get it? I got it? Okay, thank you. In the GaN and SiC designs within the power industry, is this a primary focus within end customer design and implementation? Who would like to start?
Maybe I can start. When I saw this question first, the first thought to my mind is like, I think I have been answering this question for 3-4 years. And at the beginning, the question was because most people using GaN or SiC, they were thinking to drive at 1 megahertz, 2 megahertz. Then there are like difficulties at that levels. The reality is that we haven't seen that yet a lot. I mean, of course, there are a lot of IEEE publications of 1 megahertz, but the reality is that people is still driving at even maybe 1 megahertz is okay. But then there is no problem with the magnetic cores. Let's say I'm not afraid that we can run with ferrites and it's working perfectly. What is really the big problem is that, especially for transformers and inductors, is proximity losses. Of course, that when you increase the frequency, when you try to integrate everything, there is one point that the simulation of the AC effects and the proximity losses is logarithmically complex. So at that point is where I would say you can have a very accurate models for predicting losses in all the cores for every situation, but if you are not you're not lucky and you have good models for the winding losses, everything can burn. And this is for transformers and inductors. For common mode chokes, I think that is depends of the standards, but some cases the standards are even limited for low frequencies, so no big deal there.
I think it's well said. You definitely have to balance that trade-off of winding to core losses in your design, but what I would add is that with GaN and SiC coming in, obviously you're not just pushing your frequency of the converter, it means that the switches themselves can't really survive hard switching for extended periods of time. And that then adds an additional design constraint onto magnetic converters because you generally want to have soft switching to accommodate that, which means now you have to design an inductor or a leakage transformer to have sufficient energy stored throughout your switching commutation so that you can soft switch, which is just something that you'd not have to consider 20 years ago in an IGBT design.
That gave me the idea of what you said. Something that I have seen in a lot of LLC with GaN is that really they have a huge series inductance for storing the energy and doing the resonance. And this inductance that is in series there, and we try to use like putting in the middle of the transformer, we have a problem that is really storing energy. Yeah. Then when you make the numbers of energy in joules, it's not an easy thing to solve.
I can make a comment. So I can give you a few examples. Like 10 years ago, I was designing a megawatt silicon carbide inverter for solar applications. So the intention is to try to increase the switching frequency, but the bottleneck at the end of the day is that you cannot design a huge megawatt inductor with like a 8 or even 10 kilohertz switching frequency due to the insulation design challenges. So I think like from the industry application point of view, I do not see a new core material that is needed for this application so far. I know like academia has been doing like a very high switching frequency, which may require a new like core material. But for the industry application, I think it's still like a traditional core material can still handle it, but the design has to be taken care of very carefully. And also, I think the common choke is definitely one of the big item that's like the industry is handling, especially like for the silicon carbide again, like for the products like we are building at the Lunar Energy, we spent like 7 months to handle the EMC problem because it's so difficult. And then whatever like a technical you think it will work, it may not work anymore. So you have to really like rethink from the system perspective and make it working. So definitely, I think people has been talking about reducing the size of the magnetics due to the high switching frequency, but that is not always true, in my opinion. Yeah.
I think you touched on a good point that while simulation of magnetics itself has improved, it's still really a difficult challenge to design for EMC filtering and to predict and then design your common mode choke and model it ahead of time on how it'll behave. Still a very physically iterative process of sitting there and just until you get it.
And the curve of the size of the magnetic decrease with the frequency until a specific point where it starts increasing again. It's like a UFO. But maybe the audience can help us with this. What about the common mode chokes? I mean, because I think that what I have seen is that a lot of people that is like, okay, what common mode choke should I choose here? Then you choose the current just to don't burn out, and the impedance maximum as possible, or what do you guys think? One from the audience.
Well, in order to keep the choke size reasonable, usually try to use 2 chokes with X caps, sometimes 3 of them, one in front, one in the middle, and one on the outside. So you distribute the impedance rather than trying to lump it all into one. That's the usual practice that I've seen.
I think on that too, you're also able to have 2 chokes targeting different frequency bands.
Yes.
I'm sure at Arrow you sell a lot of models of that.
Always be closing. ABC, guys. Next question. How do you see AI and machine learning technologies influencing the future of power electronics design and implementation?
I will start first. Like even in the academia, you will see this one. Like in IEEE Power Electronic Society, there's a design automation committee, which is formed probably like 3 years ago. Essentially, try to look at the problems similar like this. So essentially, instead of a non-iterative design, you want to see whether you can automate your design, and definitely machine learning AI plays a role there. I know Chema has a company that is working on this. I think in my opinion, the key challenge is that in order to be differentiated, you want to own your own database. You want to optimize per your products. You don't want to use a tool that everybody can come up with the same design. Then it will be difficult for you to differentiate. So I think that is AI machine learning is good, but it really come down to your own products, your own targets, so that you can better use these methods.
Very interesting about your own database for data. Well, my point here is that I think that within the next 10 years, we will be able to design a complete power supply assisted by artificial intelligence tools. The key, at least what I think, the key that is really going to help us to do something different is that the connection with the production. I mean, if we really can do something, I mean, if there can be some AI tools and models that can help us to make designs that are really connected to the production and really create the things from software to hardware in a direct manner, we are just breaking a big wall there. Then it's like, in 10 years, software tool for design the power supplies and connect it to the factory. That could be great.
I'm pretty curious to hear some examples of what you could see happening. Do you mean to iterate a couple of designs on AI and then sort of have them automatically produced, or?
I don't think that something that in the academia and at least we have been discussing a lot is about what is the AI really doing? It's like, do you use the AI for solving statement equation? You don't need it. Do you need AI for solving an equation that is already very well modeled? You don't need it. What you need to do is a lot of tasks that at some point you are able to define. Before the task, you can define like, okay, I want to do, I want to make a SIP analysis between 10 topologies with all these characteristics, but I want you to take in consideration that I want to keep this price or everything below this price. In this analysis, also, I want you to check the availability of the, stock, or whatever. I mean, a lot of options that give you a vision about what is the next step that is really going to help you in the connection to the factory. But simulation-wise, there are pretty good tools already. What we have to put is these tools to work for us.
So just more on the speeding up the iteration process of sweeping through designs much quicker.
Yeah, that's my point, yeah.
Actually, this is a very dangerous topic. We know the AI and machine learning are going to replace the software engineers.
Yes.
I feel like this is a topic that's we may lose our job. So
I have future proof.
Force.
I have migrated my marketing practice to hardware engineering, as you can see. Yes.
Please tell me how do you define artificial intelligence? It's a very wide definition. It can be from a very small algorithm that corrects itself in the loop. It can be easily usable in any power electronics. It's not just one word. Everybody says AI, AI. But how do you define AI is what?
I think that actually AI, we have been using AI like in our life like 50 years. I mean, what I like is when I go to my house and my dad asks me like, "Hey, what is AI? Tell me the truth." And it's like it's a software that is able to learn, and the what means learn.
Yes, means that it improves its results. It goes to the loop and improves, learns. It is used even now. When you are using the loops in your algorithm, you improve, reduce your error. That's the same thing.
Yes, but in sometimes you don't need to use AI for improving a result that is already perfect, but you can use for accelerating the process. For example, there are a lot of models in power electronics that are physics and are very well defined the model. But running like hundred of these equations and finding a Pareto from is very complex. But if you have a system that allows you to, like a ChatGPT, say, okay, can you find for me the minimum point of these inputs and these outputs and these limitations, is going to you can take a beer and the machine is doing the AI or whatever. But I think that the definition of AI is like AI, machine learning. Actually, I'm not really able to make the differentiation between AI, deep learning. I don't know. All the words.
Different. The scales are different. Can be in a smaller scale, using for a smaller task. Can be a bigger scale, as you said, very more complicated. But it's the same thing.
Exactly. It's exactly the same thing. And in some cases, you don't need even just for learning. It's just for accelerating a process.
Yes, and the same. Even in power electronics, the same things may happen.
Yeah, I'll give you a bad example to you. In my opinion, AI is something like you don't know. Let's just say if you have inputs, you have outputs, you don't know like what's the mathematical equation in between. Do you want to train your inputs output data and without knowing what's in between? However, I think for most of functions problems, like it's very well defined. I have seen people say put a buck converter there, train it. Why do we need to train a buck converter? Like I have an equation for it. Like what are you trying to train? So that is the wrong direction of using AI for nothing. Yeah, but if the equation is not so simple as like a 1 over d whatever, then if equation is like 10 equations need to try. If you need 10 equations to address a optimization problem, then I think it starts to make sense to use AI so that you don't need to find that's a single optimization point, which might be too difficult to find. So I think my point is I have been seeing people using the AI just for the sake of using AI, but that is the wrong direction, in my opinion.
I can definitely see it in like complex control applications, as you said, for like a Pareto front. I guess if you're having different switching frequencies come into play, different like duty cycles for different sides of a bridge, or multiple bridges. If you've got like a multi-active bridge topology, then that becomes a very complex mathematic, and perhaps you need to have multiple equations you're modeling, and yeah.
I think that we're at a point in the history, like maybe 10 years ago, that when I was doing the PhD, I lived with a guy. He was doing machine learning, but he was building FPA hardware for accelerating the algorithm of training. So they were like the computing power. He doesn't have the computer power to really do what he wanted to do. Then at some point, Amazon Web Service appear and all of their servers. Then you can use them, and you don't need to be like your own server at your home. So training is just not a big deal. The hardware for training is not a big deal anymore. So people is training the DC resistant calculation. So it's like, as you say, it's like using just for the sake of using. There are some points here, in in the models of magnetics, the only ones that they have seen that make sense, and we have tested and using, is leakage inductance, parasitic capacitance, and that's all. I mean, the rest, you need a lot of modeling for understanding what is happening. If not, you are losing the control, and at some point, you are not able even to verify or even to disclassify if their solution is good or not.
I love that you guys think that you're so different from software developers, but we can easily spend 30 minutes in this group or in that group arguing about what is AI and what is not AI. So you're actually very similar in that regard. The next question, unless anybody wants to raise their hand and ask something that they've been inspired. Oh, we have one. Okay, here we go.
So, are there any tools available already? Any startups working on something related to generative AI for power electronics? I mean, so many people are here. So, if someone knows anything about it, which we can follow, or any startup, any companies? I mean, in fact, Frenetic has .ai already. So,
I mean, every time my friends told me that every time I try to do advertisement today, I need to drink a beer. I already drink one, so I mean, I think that we are using that part, but I think that we are not. We are just focused on the magnetics. So I guess that I suppose that there are people doing a lot of things in other areas, but I think that there are a lot of people in academia. What I receive is a lot of people from academia doing some stuff in AI. I don't know, you guys.
I think like you mentioned generative AI, that is a buzzword like everybody's talking about. Like my brother works for like BCG. He's a consultant. He even talks about it. Because within the BCG, everybody needs to talk about generative AI. Otherwise, you are not an expert. Like in my opinion, it's like for the power electronics, like you don't not need necessarily to do a very complicated AI algorithm. You can do something like a light AI or light machine learning. Because it depends on your needs. Like there's a trade-off between the processor you can use versus the task you want to achieve. If this is for autonomous driving, you can afford a very powerful processor. You can run lots of data on it, and it will give you the benefits. But if you are only going to control inverter, and you put like $100 like a microcontroller there, and try to achieve a simple like a sinusoidal output voltage, then doesn't make sense. I think it's like like what type of AI you want to use depends on your target application. You can use like a certain portion of it, still gets your like a desired output.
And we haven't talked a lot about the assistant, but I really think what I was saying at the beginning about within 10 years, all of us will be using AI in the design of power supplies. I was referring more about assistants, about tools that allows us to really ask for assistance for doing some, let's say, simulation, sweep analysis, finding solutions, and then go to the production, because there are logistics connected and everything is connected, and we are able to. And this is AI. Well, it's software online connected with a lot of servers connected through the wall and stock and.
I'd love to ask about what process you follow to get magnetic suppliers and which ones do you recommend?
I mean, who's in the room?
There we go.
For suppliers, I generally like to go to industry events and meet sort of more niche suppliers. Ones I would recommend, like DMEG, DMEGC, and NCD, both sort of out of China. I find they have fantastic sort of materials, very good design support. Yeah.
Maybe the people from Arrow also has something to say here. Cannot say anything. We are a supplier.
Number of magnetics suppliers, so quite an assortment to choose from.
I don't want to comment, otherwise my supply chain team will be mad at me. Because I always have different opinions with them. So I want to choose one supplier, they want to choose a different one.
I respect this.
I received a funny fact about this question a few days ago because a customer told me like he was mad with the supply chain guy because he said, which magnetic should I buy? This one from this supplier or from this other one? And it's like, price is similar, but it's like, well, what do we have from the supplier? It's just the drawing, and the pinout is the same, and the same. And it's like, well, how can I decide which is better? And the supply chain guy said, you are the expert. And it's like, yeah, but they didn't give me anything. So it's a tricky question at the end. So there is a discussion about who should decide which suppliers you work with and what information do you need from the supplier. No?
I can touch on this topic. Any authorized distributor is going to hold a bunch of suppliers on demand, but as we saw in COVID-19, 52-week lead times, and just kind of, can you sign an NCNR and get it later? What we've noticed a lot of supply chain people doing is adding multiple suppliers, not having one source, and leveraging all the authorized distributors. Use Arrow, use DigiKey, because some of these guys have shorter lead times and they have better connections with the direct manufacturers. And if you really need to go to a broker, then try multiple. Never just use one, because we're seeing a lot of the same supply chain problems everywhere. But if you go to the largest broker, they have the largest network. And you'll notice a lot of people hoarding electronic components at the moment. We're calling it like the largest excess event we've ever seen. These people were hurt during COVID-19. And a lot of big authorized distributors made you sign those NCNRs, and now they're shipping that product, and you don't need it anymore. And you overpaid. They don't care. They just want to sell you the product. Brokers will actually buy it back at least, and we'll wait for the next event. But that's just my opinion.
Thank you. I've never listened to the word broker for this kind of people.
As a manager or a team lead, striking a balance between maintaining control and effective delegation is crucial. How do you approach delegation to ensure that tasks are assigned appropriately without falling into the trap of micromanaging? Can you share specific strategies or experiences where you successfully empowered your team while maintaining oversight?
Yeah, I will start first. Yeah. So my overall philosophy for this one is that you have to put trust first until the trust is no longer there. So for the if let's say if I trust someone and someone can prove that they can do it, my overall thing is that I will tell them direction where I want to go, and you go and get it. But for the team members who are not meeting the expectation, then I will need to have more closer mentoring for them. And then of course I'm not going to put them on the critical task, so that I don't need. Otherwise I will spend more than 50% of my time on them. So you have to pick the high performers, and then rely on them, put the task on them, and then trust them, and they will deliver for you. That's my overall understanding.
I think that in the way I organize these kind of things is, okay, you need someone to do something. Then first thing is you have to really know what do you expect. It's like, okay, an electrical engineer, and he needs to, I don't know, run simulations and build a power supply, blah, blah. So in that case, there are like four levels of knowledge or mastering skill. The first one is unconsciously incompetence. It's like you don't know what you don't know, and you need a lot of micromanagement. You need step by step to show you what is. Really the basics. Then there is the next level that is like you are consciously incompetent. You know, like, hey, I know that I need you to train. To review my steps. Then there is like the next step is like where you are competent, but it's like not fully competent. Then it's like, okay, we can have weekly reviews. Okay, you are ready to do the task. You know what to do. You know where you have your weakness, and I can review your task. And then there is a funny thing about the unconsciously competent. People can do it without even thinking, because they are automatically, it's like I don't know, someone doing the bread, very good bread. I mean, the people doing the tacos, they were not thinking that they know probably how to do the tacos, but they know how to do the tacos very well. So there is one level where you already are mastering something, and even you are unconscious about that you are mastering that part. So if you are able to define this or the person, then you can say, okay, you need micromanagement, or you need a weekly review, or yeah, this is the way I organize.
I think I've only had sort of contractors or sort of technicians as direct reports, or sort of indirect reports. So I would sort of want to direct my question at you. Put more on your plate. How would you differentiate between when you decide to give someone a little bit more feedback or more micromanagement, and between sort of telling them the direction you want to go in and then trusting them to let them do it themselves?
Yeah, I think for me, it's like, although I said like put trust first, but you have to give the small task first to see whether they can deliver. So I have a few like criteria that I think I would say, like if I see a very strong performer, there's a few things they need to do. One is that like when they say they can do something, they can deliver. When they face a challenging, they will let me know. And the other one is that typically that is really differentiates the good engineers and the average engineers, is that if this is going to be like a non-pull task, like if you have to do something for more than a few months and you have to address it, can you survive? Like many smart guys can figure out the problem within 10 minutes, say, I got the answer. But sometimes the problem is so challenging that like you have to spend months of time to address a single problem. And typically when I see those kind of employee, I'm going to put them in a very important task. The reason is that if I'm going to put someone as a future leader position, if there's a difficult problem, if they say, okay, I'm going to quit, then that's not going to be good. But if they can like show the resilience, and if they can survive, they can also guide their team to survive. So I think like to me, it's like start from small tasks and then difficult one, and then end of the day I want to see how like persistence and how resilient they are. So that's like I work in a startup. This is the most important thing for me. Like I want to see the strong performers who can not only like perform the task, who can also like perform a difficult task for a very long time, who can also influence the colleagues around them.
How many of you are at a startup, by the way? Can I get a show of hands? Very, very nice. I love it. The pace of work is very intense. So in the interest of time, I would like to have one more question, and then we'll move to the tech talk so that we have just enough time to eat the remainder of the food, drink the remainder of the beer, meet everybody now that you have a better familiarity of who's on stage, and, have a safe trip home, basically, right? So bear with me as I skip to my last slide. Okay. Pros and cons of off-the-shelf magnetics versus custom magnetics. When do you do off-the-shelf? When do you do custom?
I personally like to start with off-the-shelf for early prototype designs. Obviously, my current role and in my previous one as well, we had larger manufacturing, so starting with a baseline is really helpful. You can get a good feel to see if your initial pass of the design made sense, and then from there, going custom, whether that's fully custom core, custom winding, everything, and then getting the manufacturing done from there.
I keep my answer for the tech talk because I'm going to talk about something similar.
Yeah, for me, it's like if you can buy the off-the-shelf components that can meet the requirements, you want to leverage the volume, so you can buy it. But most of the time, like for functions like a power stage design, you don't want to do that. Like you want to optimize, global optimization for your switching frequency, for your like operating points. So like I don't think you can rely on the off-the-shelf components. And I don't think there's anybody who can offer that one to you.
I'd like to take this opportunity to thank our panelists for their time and expertise today.